let's look at some example problems. The knapsack problem is a well-known, famous problem in computer science, and it is often used in undergrad education, and therefore we'll just review it here and use it as an example for integer programming. As input, we have a set of items, and I is the index of an item, and the item I has a value vi and a weight wi. So v stands for value and weight, w stands for weight. And then we have a knapsack with a maximum capacity of C. The goal now is to pack a subset of the items into the knapsack such that the sum of weights does not exceed the capacity C and that the sum of the values is maximized. Let's look at the example on the next slide. So this is the capacity C of the knapsack. So this blue box is an abstract representation of the knapsack, and the capacity C is not given as a volume, but it's given as a maximum weight. So the items that we pack cannot exceed the weight of 10. We have 3 items, and the first item has a weight of 5, the second item has a weight of 8, and the third item has a weight of 3. What we're able to do now is think about different combinations of items that we could pack into the knapsack. For example, if we wanted to pack all 3 items 1 to 3, then we would obtain a weight of 8 plus 8 is 16, so this would exceed the knapsack capacity. If we would maybe do this greedily, we start with item number 2, so then we have a weight of 8, then we couldn't pack any more additional items. If we start with maybe item 1, then we can pack item 1 and item 3 together, so then the weight is 8. This also doesn't exceed the knapsack capacity. To evaluate which combination is best, we have to look at the values. So if we only pack item number 2, we would have a total value of 7. If we pack items 1 and 3, then we would have a value of 3 plus 5, which is 8. So packing items 1 and 3 is better than only packing item number 2. Now let's look at the formulation of this problem. As variables, we use variables xi, where xi equals 1 means that we pack item number I, and xi equals 0 means we don't pack item number I. The variables xi are binary, so we have the constraint that xi have to be either 0 or 1. Guess there should be some bracket here, but alright. The objective is we would like to maximize V transpose X or minimize minus V transpose X. That means for all items that we pack, the component in X will be 1, the corresponding one, and then we will add the value to the sum that is computed by this inner product. We only have a single constraint, W transpose X smaller equal to C. So how difficult is this problem? This problem is already MP hard. However, it's not an especially difficult problem nevertheless. For example, for integer weights and integer capacity, a dynamic programming solution exists, and then the problem would be pseudo-polynomial. Now, in addition, very good heuristics exist. For example, one could just pack items greedily, trying to select items that have the best ratio between weight and values. So we want to pack the items first that have the most value per weight. Also, in general, this heuristic will give a very good approximation to the problem already. Here's an example of Matlab code to implement this knapsack problem. First, we set the knapsack capacity C, then we have a vector of weights, a vector of values. These are things that need to be given to specify the problem. There are some details in how the variable types are specified, and that we're going to skip here. So we'll just look at the formulation. Okay, we'll take the time with tick and tock, and then one can call int limprog, and then one hands over the weights. Again, this transpose is some detail, the values, and the capacity, and also these other things here and here are just some details of the interface that we're going to skip. So here I copied the code into Matlab, and then we can run it. All right. So what we see here is the optimal objective value, and there are some details about the cuts, some heuristics, and then here we find the answer that is computed that tells us which of the items is packed, that is where the components where we see a 1, and which are not packed, these are components where we see a 0. And we see for this small number of items, this works still very fast, under 1 second. Next, we're looking at the map labeling problem. We have a set of map objects where I is the index of a map object, and where each object has a discrete set of possible label positions, j. Then there's a cost c for each label placement. And all these costs together we could write in a vector c. The goal is to place at least one label per object without overlap. For example, there could be rivers and cities that need to be labeled on the map. So we have one city, this would be the city 1, and there are 4 possible placements for a label, maybe the city name. So we have x11, this is the variable corresponding to this label placement, x13 is the variable corresponding to this label placement, and then we also have these 2 possible label placements for the first city. For the second city here, we have these 1, 2, okay, I didn't go in order, 1, 2, 3, 4 label placements, and then for the river, there's maybe only this one label placement. Maybe for the illustration would make more sense if there's maybe some other label placement as well. So these variables x subscript ij mean that if xij equals 1, that means that the label for object I is placed in position j. So for this city 1 here, there are 4 labeled positions. So the first subscript is the object number, object index, and the second subscript is the index of a position. For the second city, we also have 4 possible placements. The difficulty of the problem arises because some of these possible label placements, for example these two, overlap. So it's not possible to place the label for city 1 in this position 4 here, while at the same time place the label for city 2 in this position 1 here. Also, the costs now are per possible label placement. That means the placement x11 might have a different cost than the placement x12. You could think of this as maybe there is some general preference by a map designer, or someone did a user study that said that people prefer labels to be on the top right, and in the worst case they should be on the bottom left. So this could express some preference in the design. Alright, next let's look at the constraints. First, all variables x, I, j need to be binary. Then we have a coverage constraint, at least that's how I call it. That means that each element, each city, each river needs to be labeled exactly once. So for all I, just imagine we keep I fixed, so we sum over all possible label positions j, and the sum of this xij equals to 1. We have one such equation per object in the map that needs to be labeled. Then we need to model this issue that there has to be no overlap between conflicting placements. Now this is a geometric component that cannot be simply derived by the mathematics. One would have to look at the map and actually check geometrically which label placements are possibly overlapping or are overlapping, and then for each pair of such overlapping placements, ij and lm, we need an equation that says that maximally one such label can be placed. And we model this by xij plus xlm smaller equal to 1. Finally, we have some objective that we would like to minimize the overall cost. So we have the minimum, and then we sum over all variables xij, and we compute cij, the cost of the placement, times xij. Whenever xij is active, that means xij equals to 1, then the cost will be incurred, and if xij is 0, then the cost will not be part of the sum. Next, we're going to talk about the assignment problem. We have n people that are tasked to carry out n jobs. We need to model how suitable the people are for particular jobs, and we do that with a cost. So there's a cost Cij, that is the cost for assigning person I to job number j. The goal is to assign each person to exactly one job so that each job has one person assigned to it. What we see in this illustration below are the people on the left side and the jobs on the right side. So we could have person 1, 2, and 3, and job 1, 2, and 3, And then for every combination of person and job, we have a cost. So for example, in this edge here, and with this numbering, we would have this Cij is C23. That would be the cost of assigning person 2 to the job number 3. As variables, we have xij equals 1 if person I is assigned to job j, and xij equals 0 if person I is not assigned to job j. The objective is to minimize the sum over all xij times Cij, the cost. This is identical to what we had before. Every time xij is 1, that means that Cij will be part of the sum. Now let's look at the constraints. We have a binary constraint that all variables xij have to be binary. So xij has to be an element of the set 0, 1. Then this is a constraint called limited work. Each person I does exactly one job. So it is not possible for a person to be either idle or do more than one job. So for all I, we have the following equation. So if there are n people, that means we will have n equations of the following form. The sum of xij over all j equals to 1. So for the person, for example, for the person 1, we will sum up over all variables x1j, and the sum is j equals 1 to n, since we have n jobs and n people. So we will have n equations that consist of a sum that has n elements. Then we have a coverage constraint, and the coverage constraint says that each job is done by exactly one person. We do have one such constraint for each job j, so that means we have n such constraints. And the constraint is the sum over I xij equals 1. So for example, for the third job, we would have the sum over xi3 equals 1. And then this sum here has n elements, and again we have n such equations. Now, what happens if we don't have the coverage constraint? Each person will do exactly one job, but that doesn't mean that one particular job doesn't have more than one person doing it. Just multiple people, maybe person 3, 7, and 5 might all decide to do the job number 1. What is the difficulty of the problem? While we formulated the problem as an integer programming problem, there are specialized algorithms that are most likely more efficient. So an implementation of the Hungarian method, also called Kuhn-Mancras algorithm or Mancras assignment algorithm, that's probably the most popular method, but there's also auction algorithms. So this shouldn't be a claim of which method is better. It's just that the Hungarian method is often something that is taught maybe in an undergraduate degree of computer science. I still think it's interesting to start with this assignment algorithm formulated using integer programming, because there are many types of layout algorithms that then introduce variations and additional constraints that can be understood using this assignment algorithm as a basis. So let's look at an example here that is a tourist map layout problem. As input, we have an overview map with points of interest that we call POIs. Think of a tourist map of a city like Paris, and the points of interest are the major sites that the tourist might want to see. Then there are detail maps for each point of interest. Further, there are possible positions for the detail maps, and a cost Cij for assigning a POI I to a detail map position j. So POI I assigned to detail map position j. And the goal is to assign each detail map to one position. Here's a visualization. We have the points of interest shown as orange circles. So maybe this would be 1. Let's say this is 2. This is 3. And then at the bottom, we have possible positions for detail maps. The detail maps are shown on the right. You could think of this as maybe some additional information or like a local map where the point of interest can be located, maybe opening hours or something could be written there. And what we see here is that not all detail maps necessarily have to have the same size. So the map M1 here is twice as big as the maps M2 and M3, and each of these maps corresponds to one point of interest. Now we can look at the variables. We have variable xij equals 1 if map I is assigned to position j. So we would need to also number these positions, maybe 1, 2, 3, and 4. So if map number 1 would be assigned to position 2, then x1, 2 equals 1. The objective again is to minimize the sum over all xij times cij, where cij is the cost. Let's also discuss the constraints. We have, again, binary constraints. Xij have to be either 0 or 1. Each map I is assigned once. Therefore, for all maps, so for all I, we have this equation that the sum over xij equals 1. There will be one such equation for each point of interest, which is the same as for each map. Then there can be no overlap between maps. So we have for each position j, we have an equation that is that the sum over all xij equals 1 for all pairs ij element of some index set. While this equation is again very, very simple, it encodes some geometric knowledge that is not visible here in these equations. One has to construct geometrically these pairs. So this OJ is a set for the position J that has all placements that overlap in this position. And the tricky part here again is that some maps can cover more than one position, even if they're placed in a different position before. Let's look at that again in the visualization. Again, let's assuming this is POI number 1. If the POI number 1, we have this assignment here active, then the map number 1 would be placed over these two positions. So that means if x1, 2 equals 1, so if this gets assigned here, then x1, 2 equals to 1, but that now precludes other POIs to use this position number 3 here. So again, this was position number 1, this here is position number 2, this is position number 3, and this is position number 4. So if x1, 2 equals 1, then it's not possible that, let's say, maybe this is POI 3, x3, 3 equals 1. And this is some geometric analysis that has to be performed to check which possible map placements are in conflict with each other. Now, let's look at tiling. As input, we have a set of tiles I and a domain consisting of positions j. We have a cost, again, Cij, for assigning tile I to position j. Optionally, we might have a minimum and maximum number of times that the tile I is allowed to be used. This can be encoded by the numbers min I and max I. Two such numbers could be given optionally for each of the tiles. The goal is to cover the domain with the given tiles. To the left, we see 3 example tiles, and we choose them from the Tetris tile set. To the right, we show the domain as a regular grid, and what we see here is the assignment of one tile, this is this last tile here, to one position in the grid here. Again, there is some geometry to the problem, so we need to have some way of specifying exactly what the tile placement means. So what we need is, for each tile, we need some designated little square. So in this tile, it's maybe this one. So then for the other ones, maybe for the first one, we could say it's this one. And for the second one, maybe we'll pick this one. So what an assignment would mean is that the first, or this designated square, is placed at this grid cell. And if that happens, then we say that tile number, I don't know, let's say this is I, tile number I is assigned to this position here. This is position j. And then due to the geometry of the problem, if this assignment happens, the tile would actually be placed over these 4 positions. So that every tile, since every tile consists of 4 squares, if there is an assignment that is made, then the tile covers 4 positions. So our variables are xij equals 1 if the leftmost square of tile I is assigned to position j. Again, we use I as the index of a tile and j for the positions. The objective is the same as before. We sum up over all variables xij multiplied with their cost Cij. As constraints, we have the following. There's a binary constraint. All variables have to be binary, either 0 or 1. Each tile is assigned within its allowed limits. So the sum over j, this is sum over all positions, of xij has to be between min I and max I. We have one such an equation for each tile I. This part is optional. Further, there can be no overlap between squares in the domain. We have one such overlap equation for each position j. So for each position j, we sum up over all variables xij that could cover this position j. And again, looking at the geometry of the problem, we need to identify all the tile placements where one of the squares would cover position j. So there would be this index set Oj, where this set contains these pairs of indices where the corresponding tile placements overlap position j. Another example would be shape matching, or at least simplified shape matching. As input, we have two shapes where each shape has n vertices. There's a cost Cij for assigning vertex I from shape 1 to vertex j on shape 2. The goal is assign each vertex on shape 1 to exactly one vertex of shape 2. A simplified version here could be formulated as the assignment problem. So the problem here is that there would be, in real life, an additional goal that close by vertices on shape number 1 would be mapped to close by vertices on shape number 2. Modeling this is a lot more difficult. We might come back to this later in this tutorial. Let's look at the camera placement problem. As input, we have a domain sampled into positions P. And then we have a set of possible camera positions I. The goal is to select a minimal set of cameras that cover the domain. Here we see the domain, and the domain is discretized into grid cells, and we have three possible cameras here: camera 1, 2, and 3. So for one camera, as shown here for camera 2, there would be a field of view that this camera can see. So all these cells, let's say if this view of a camera covers the center of a cell, then we would say that the camera sees this cell. To model this, we use the variables xi with xi equals 1 if the camera position I is selected. The objective is that we want to minimize the number of cameras, therefore we want to minimize the sum over xi. As constraints, we have the binary constraint. Xi has to be a binary variable for all xi's. Then there is a position conflict constraint. Let's say that there would be some positions that are conflicting so that a camera couldn't be placed at both of these positions at the same time. Or there might be even a larger set of cameras, that means a larger set of camera locations where only one of them can be selected. So this could be modeled by some set Ni, that is a set of locations that conflict with location I. So for all locations I, we have one such constraint, the sum over xj small or equal to 1, where j has to be an element of this index set. all the visibility equations can be written as once as v times x greater or equal to 1. That means that the ith column of v is a binary mask that encodes what position can be seen by camera I. Just to review some basic linear algebra, so V would be a matrix and it has as many rows as there are positions in the discretized grid, and one of these columns corresponds to a visibility mask for a particular camera. So let's say this is the column in the matrix that corresponds to camera I. And then this matrix is multiplied with a vector, and if the ith element here of the camera, so the ith camera is selected, then this column will be active, and all these elements will contribute to the visibility. So what we want to have in the end is that this is greater or equal to a vector of all ones. Again, to review some linear algebra, any element that is selected here, so that any variable in this vector that is 1, will activate one of the columns. And then if we take this sum of the columns, of all the active columns, we would like to guarantee that in at least one of the elements per row is 1. This will guarantee a coverage of the complete domain. Another remark, a difference to tiling before, is that here we allow a view to cover a position and then another view cover the same position in the domain. So each position in the domain has to be covered at least once, but it